This might be the biggest misconception in introductory statistics. Most people think, if my data isn't normally distributed, I can't use the bell curve. But one theorem completely changes everything. In fact, even if your original data looks nothing like a bell curve, the averages often do. And that idea powers almost all of modern statistics and a huge part of machine learning. Imagine 3 completely different data sets. One is uniform, one is heavily skewed, one looks almost random. None of them resemble the famous bell curve. So, which one do you think will eventually produce a normal distribution? Surprisingly, all of them. Let's try something. Instead of looking at every individual value, we randomly choose 5 values. Then calculate their average. That's one sample mean. Now let's repeat this experiment again and again and again. Look carefully. The original data is still uniform. It hasn't changed, but something amazing happened. The distribution of the averages is becoming normally distributed. We didn't change the data. We only changed what we were plotting. Instead of plotting individual observations, we plotted their averages. And suddenly, the bell curve appeared. Maybe that only worked because the first dataset was uniform. Let's try the skewed one. It happened again. The original data stayed skewed, but the averages became increasingly normal. 3 completely different datasets. One identical result. That can't be a coincidence. This phenomenon has a name: the Central Limit Theorem. It says, if you repeatedly take random samples from almost any population and calculate their averages, those averages tend to follow a normal distribution as the sample size becomes large enough. This single idea explains why the bell curve appears everywhere. Not because everything is normally distributed, but because averages often are. At the end of part 1, we saw something interesting. As the sample size increased, the bell curve became smoother. But something else happened too. It became narrower. Why? Imagine estimating the average height of students. If you randomly choose only 5 students, your estimate could easily be too high or too low. But if you choose 100 students, your average becomes much more reliable. Large samples are simply less noisy. Bigger samples don't change the true average. They just make our estimate much more stable. If you've studied statistics before, you've probably heard this. Use a sample size of 30. But why 30? Is there something magical about that number? Not really. 30 isn't a law, it's a rule of thumb. For many real-world datasets, a sample size around 30 is often large enough for the sample means to start looking approximately normal. Some datasets need fewer. Some need many more. 30 is simply a practical guideline, not a universal rule. Here's something even more surprising. The shape changed completely, but the center didn't. The average of the original population and the average of the sample means are actually the same. The Central Limit Theorem doesn't change the average. It changes the distribution of those averages. That's why we can estimate population averages using only a sample. And that's one of the reasons statistics is so powerful. A factory produces light bulbs. The lifetimes are heavily skewed. An engineer randomly samples 50 bulbs and calculates their average lifetime. Will these averages be approximately normally distributed? Many beginners assume no, because the population is skewed. But remember the Central Limit Theorem. Take many samples of 50 bulbs. Each sample produces one average. The averages slowly form a bell curve. Even though the original data is skewed, the distribution of the sample means becomes approximately normal. So the answer is yes. Why should AI engineers care? Machine learning rarely trains on one data point at a time. It trains on batches. Every batch produces averages, average loss, average accuracy, average gradients. The Central Limit Theorem explains why these averages behave so predictably. It's one of the mathematical foundations behind statistical inference, confidence intervals, and even many optimization algorithms. Without the Central Limit Theorem, modern statistics would look very different. Let's summarize. Original data does not need to be normally distributed. Random samples produce sample means. As sample size increases, those sample means become approximately normal. Larger samples produce more stable averages. That's the Central Limit Theorem. True or false? The original population must be normally distributed for the Central Limit Theorem to work. False. Increasing sample size generally makes sample averages more variable or less variable, less variable. What does the Central Limit Theorem describe? Individual observations or sample means? Sample means. Here's the one sentence to remember. The central limit theorem isn't about the original data. It's about what happens to the averages. Congratulations! You've just completed one of the most important sections of statistics. From here onward, we'll stop asking what is a distribution and start using distributions to answer real questions about data. That's where statistics becomes incredibly powerful. Next time, conditional probability, the probability that changes when you learn something new.